Hello, everyone. Today my topic is generalizable close manipulation with large language model. Firstly, let's review the existing work. Recently, there have been some learning algorithms that can enable the robot with advanced close manipulation ability, like fold the t-shirt, hang the towel, and flatten the t-shirt. These methods are task-specific, which means their algorithm can only perform on a specific task. However, training a separate model for each specific task is inefficient and not practical. So our motivation is to achieve generalizable close manipulation. Generalizable close manipulation means the robot can perform well on diverse tasks and generalize to new object categories and new task requirements. For example, transfer the skill from a t-shirt to a skirt, or from folding a towel in half once to folding it twice. How to achieve generalizable close manipulation? There are two technical challenges. The first one is close have high dimensional state space. The second one is sequential action inference for different tasks. To address these two technical challenges, let's think about a question: how do humans manipulate clothes? As this video shows, we only manipulate some significant geometric features like sleeves, so the action space is not on the whole object. Besides, there are some common action primitives shared by different tasks like grasp and press. Based on this observation, we use a large language model for task planning and decompose open-world language instructions into subtasks. Each subtask is represented as an action primitive and contact point, which is inspired by the human manipulation process. The common-sense knowledge of the large language model can enable generalizable task planning. To complete each subtask, we adopt semantic keypoints as state abstraction to capture the geometry and the affordance of close manipulation. Based on this, we can achieve the visual grounding of the contact point. Semantic keypoints are independent of specific tasks, which can be utilized to ground contact points of unseen manipulation tasks. Finally, an action model is used to generate the trajectory conditioned on the action primitive and contact point. Experiments. We first compare the performance of our method with the previous language conditioned manipulation baseline. Our model outperforms the baseline in terms of success rate and generalization. Since we have used depth images as observation, the sim-to-real gap is small. Our algorithm can be directly used in real-world tasks. Here we show 3 examples. Compared with previous methods, our method doesn't need to train a separate model for each specific task. We make the robot capable of generalizable close manipulation ability. Thank you for your listening.